Could our 3D reality be an illusion, a projection of information encoded on a two-dimensional surface? This is the central idea of the holographic principle, a theory suggesting that all the information in the universe, including matter, energy, and physical laws, may be stored on a boundary, much like a hologram projects a 3D image from a 2D surface. Emerging from studies in black hole physics, the principle was first hinted at when researchers found that a black hole's entropy, or information content, is proportional to its surface area, not its volume. This surprising result implies that the universe might not be fundamentally three-dimensional. Advanced theories like ADS-CFT correspondence strengthen this idea, showing how gravity in a higher dimensional space can be fully described by a quantum field theory on its lower dimensional boundary. If true, the holographic principle could unify quantum mechanics and general relativity, suggesting that spacetime and gravity are emergent phenomena derived from underlying quantum processes. Though experimental proof remains elusive, projects like the holometer aim to detect holographic noise as evidence of a lower dimensional reality. Beyond its scientific implications, the theory challenges our perception of existence, hinting that what we experience as physical reality might be a complex projection of deeper informational principles. The holographic principle not only addresses fundamental questions about the nature of the universe, but also opens a doorway to rethinking cosmology, physics, and our place in a potentially emergent reality.
The holographic principle posits that our 3D universe, including all its matter, energy, and physical laws, could be a projection of information encoded on a two-dimensional boundary. Originating from studies in black hole physics, this idea suggests that all information contained within a volumetric region of space can be represented on its surface. Proposed by physicist Gerard Hooft and further developed by Leonard Susskind, the principle aims to resolve paradoxes in quantum gravity and reconcile general relativity with quantum mechanics. In black hole physics, the Bekenstein-Hawking formula shows that the entropy, information content, of a black hole is proportional to the area of its event horizon, not its volume, hinting at the holographic nature of information. The holographic principle is like a hologram on a credit card. The 3D image we perceive is entirely encoded in the 2D surface, suggesting a similar encoding for our universe. The principle emerged from studying black holes and their thermodynamic properties. Jacob Bekenstein discovered that a black hole's entropy is proportional to the surface area of its event horizon, not its volume, implying that the information within the black hole is stored on its boundary. Stephen Hawking's discovery of black hole radiation reinforced this view, as the emission suggests a finite amount of information about the black hole's contents. This result challenges classical notions of locality and volume-based information storage. Example: a black hole with a surface area of 1 square kilometer encodes all its internal information in that surface, regardless of the black hole's internal complexity. Analogy: the event horizon of a black hole is like the outer cover of a book, where all the content information is somehow encoded on its surface rather than its pages. The holographic principle gained a concrete framework with Juan Maldacena's ADS-CFT correspondence in 1997. This theory describes a mathematical equivalence between gravity in a higher dimensional anti-de Sitter, ADS spacetime, and a quantum field theory, CFT, without gravity on its lower dimensional boundary. This duality suggests that the information describing a gravitational system can be entirely encoded on a boundary without gravity, supporting the holographic principle. Example: in the ADS-CFT framework, a black hole in 3D AS space corresponds to a thermal state in a 2D quantum field theory, demonstrating the equivalence of descriptions across dimensions. Analogy: ADS-CFT is like watching a 3D movie where all the data required for the projection is stored on a 2D film strip. the entire 3D experience emerges from lower dimensional information. Quantum entanglement provides critical insights into the holographic principle. In holographic theories, entanglement entropy, the measure of quantum correlation between parts of a system, scales with the boundary area rather than the volume. This scaling reinforces the idea that information about a system is encoded on its surface. The entanglement structure of spacetime itself may be a holographic manifestation, with spacetime geometry emerging from quantum entanglement patterns. Example: the Ryu-Takayanagi formula in ATCFT relates the entanglement entropy of a region in the boundary theory to the area of a minimal surface in the bulk ATS space, directly connecting geometry and quantum information. Analogy: quantum entanglement in the holographic principle is like a spider web where connections on the edges determine the overall structure and shape of the web, even in the absence of direct internal connections. The holographic principle suggests that the fundamental description of the universe might not involve traditional 3D spacetime, but instead a 2D quantum mechanical system. This view helps reconcile general relativity and quantum mechanics by reducing the degrees of freedom necessary to describe a system. It implies that spacetime and gravity could emerge from underlying quantum processes rather than being fundamental entities. Example: loop quantum gravity and string theory both incorporate holographic ideas, proposing that spacetime emerges from discrete, lower-dimensional quantum structures. Analogy: quantum gravity under the holographic principle is like a detailed 3D model constructed from 2D blueprints. What appears continuous and volumetric is derived from simpler, lower-dimensional rules. While the holographic principle is mathematically elegant, experimental verification remains a significant challenge. Observations of black hole thermodynamics and gravitational waves provide indirect evidence, but testing the principle on cosmological scales requires new tools. Advances in quantum simulation, high-energy physics, and astrophysical observations could eventually reveal holographic signatures in spacetime structure. Example: the holographic noise experiments conducted by the holometer at Fermilab aim to detect quantum-scale fluctuations in spacetime that could support the holographic model. Analogy: searching for experimental evidence of the holographic principle is like looking for imperfections in a hologram under a microscope to confirm that the 3D image is encoded in a 2D surface. The holographic principle extends to cosmology, suggesting that the observable universe could be a holographic projection of information encoded on a cosmic boundary. This perspective reinterprets the Big Bang singularity and the evolution of spacetime as emergent phenomena. In particular, the holographic principle provides insights into the nature of dark energy, the cosmological constant problem, and the entropy of the universe. Example: the holographic interpretation of the universe suggests that the cosmic microwave background, CMB, radiation encodes information about the initial conditions of the universe on a 2D boundary. Analogy: cosmology under the holographic principle is like deciphering the content of a book from its cover. The boundary contains encoded clues about the entire volume. The holographic principle challenges our perception of reality, suggesting that the volumetric, three-dimensional world we experience might be an illusion. This perspective raises profound philosophical questions about the nature of existence, consciousness, and the fundamental structure of the universe. If the holographic model holds, it implies that reality, at its core, is informational, and that the physical universe is an emergent construct. Example: in a holographic universe, concepts like distance, space, and time are not fundamental, but are emergent properties, derived from information encoded on a lower dimensional surface. Analogy: the holographic view of reality is like realizing that the intricate images on a holographic card are not real 3D objects, but rather patterns encoded in 2D. The holographic principle opens new avenues for research in quantum gravity, string theory, and cosmology. Key questions remain unanswered. How does the encoding of information on a boundary translate into emergent spacetime? Can we reconcile the holographic principle with the observable expansion of the universe? And can this principle bridge the divide between classical and quantum descriptions of reality? Advances in quantum computing, gravitational wave astronomy, and high-energy physics could help unravel these mysteries. Example: future experiments, such as next-generation gravitational wave detectors and quantum simulations of spacetime, may provide direct evidence for holographic phenomena. Analogy: research into the holographic principle is like reverse engineering a complex machine to discover how its simplest components generate its most intricate behaviors.